Okay. All right. Well, thank you for inviting me to talk. I'm here to talk about a new research project that is just starting up. It's called SAFRR, and that stands for Socio-ecological Considerations for Sustainable Fuel Treatments to Reduce Wildfire Risk. So it fits very nicely with what people have been talking about here this morning. And this whole project kind of aligns with the National Cohesive Wildland Fire Management Strategy. And for that, the three goals are resilient landscapes, fire-adapted communities, and safe and effective wildfire response. And so with the SAFRR project, we're basically looking kind of at this broad-scale fuels management. So it's an integrated assessment of fuel treatments. And we're looking at three parts. So social acceptance, will the public accept a fuel treatment? Ecosystem services, so how can we make safe fuel treatments last longer? And protection of the built environment, so how can we make them useful for firefighting activities? So I already heard someone talk about, firefighters need to get in there and be able to use these fuel treatments. So you see it matches with fire adapted communities, safe and effective wildfire response, and resilient landscapes. And so what are we going to look at to look at these topics? So for social acceptance, some of the things that we're going to look at with this research project is, say, the type of fuel treatment, land ownership, previous experience, say, with fuel treatments or controlled burning. All those things can influence social acceptance of options to reduce wildfire hazards. As far as ecosystem services, we look at healthy forests, kind of assess healthy forests, long-term fuel reduction, wildlife habitat. So with this, we're going to be doing like grounds transects, canopy cover, collecting information that hopefully can go into wildfire modeling to look at the effectiveness of fuel treatments to reduce wildfire hazards, but also how can we create them to last longer. That's also been mentioned in some of the talks. And then as far as protection of the built environment, we want to look at installation costs, fire suppression support, how effective are they at that, and maintenance costs. How often do we need to go back in there and retreat these fuel treatments that are put in? And so there's kind of overlap among our three different Venn diagrams. So for example, if you have fuel treatments over here, you're going to have community support. It's going to reduce fuels, but it could have really high maintenance costs. Down here, the community could be resistant to it, not want it to go in. It could be very effective at reducing fuels, and the maintenance costs could be low. Up here, the community might want it. However, it doesn't really do a good job at reducing fuels, but the maintenance costs are low. And so we really want to try to find the middle here. So the sweet spot here, we get all three happening. And so when we do have the sweet spot, you have community support, low fuels, and low maintenance costs, and you can help maybe better achieve your three goals. And so in order to look at kind of the social and ecological aspects of fuel treatments, it's a 4-year project, started in December, and we're going to be including some modeling. So modeling wildfire modeling, more as part of this project. We're going to be doing vegetation surveys on existing fuel treatments and new fuel treatments. This could include manipulations, planting to try to force different successional pathways. And Melissa, after me, will talk about that. She's on the ecological team. Interviews with wildfire practitioners, some household surveys, GIS. I love GIS. So that's got to be part of it. And choice experiments to see, what are the trade-offs when people are looking at fuel treatments, what type of combinations would they accept? And then workshops, because there's a lot of activity right now going on with fuel treatments. And so our study locations are the Kenai Peninsula. We're hoping to work with the communities of Cooper Landing and Soldotna. And then in Anchorage, probably a community council around the Anchorage area. And in Interior Alaska, the Tanana Chiefs Conference is part of this project. And so we'll be revisiting a lot of the fuel treatments in TCC communities. One is going to happen in Eagle. We'll be traveling to Eagle this summer. And they're putting in part of a fuel treatment right now, and we'll be putting one in next year. And so we're trying to look at kind of before and after field vegetation in those field treatment areas. And so we have a fuel treatment database. I presented on this a few years ago. I have updated it. So with vegetation, using this Landsat above data that has 15 different vegetation classes. And so I looked at what is the vegetation composition within the fuel treatments across the state of Alaska. Also, I intersected it with the land ownership to say, you know, what lands, you can look at it, what lands are, you know, fuel treatments primarily happening on. So that is updated and it is available online for people to look at. Quite frequently people say that I'm missing things in the database. Send them to me and I can get them put in the field database. I know in the Matsu I'm missing quite a few field treatments. And you know, we're talking about vegetation succession, and these are examples of some field treatments in the Anchorage area. And you can see they were done about the same time, but they look very differently a couple of years ago when I was out there taking pictures. So as far as the ecological component, you know, we're looking at, or, you know, how do fuel treatments influence these successional pathways? And so Michelle Mack, she's going to be leading the ecological team. She's had, I think, at least 20 years of experience in field treatments up here in Alaska. And she has a team of researchers that will be going out to hundreds of sites this summer. And also I mentioned TCC is involved in this project, and they will be revisiting some of the fuel treatments that they've done around their communities to collect information as far as what do they look like now. And then there's the wildfire research team. It's called WIRE, and they're a team from down below. They've done a lot of research in the lower 48 on social acceptance of fuel treatments and fire management options. Hannah Burkett-Smith, Patricia Champ, and Chris Barth. So we have the Forest Service involved and BLM involved. And they're primarily the social side. And so they're looking at, you know, overall, they're going to start with this landscape level wildfire risk assessment. They've been reaching out to people at the Kenai Peninsula Borough, and then they'll use this assessment in combination with this parcel risk assessment that they do. So it's a census of all the parcels looking at the wildfire hazards and risks in the parcel, and they work with the community to do this. So people at, you know, the Kenai Borough will work to help collect this information, which can go into community wildfire protection plans. And then they combine this with a household survey so that they can look at, you know, on the ground assessment and a survey, and then come up with some reasonable options for how can we, you know, better prepare communities for wildfires. So, you know, wildfire adaptation, and there's an example of, you know, some of the outreach activities that have come from the WIRE team. They'll be up here this summer visiting the Kenai Peninsula in June. And so also we have some economists that will help look at those choice experiments and also mitigation, mitigation, how much it costs. Joe Little here has done some work with Randy Jant, you know, looking at homeowner preference, you know, for wildfire risk mitigation. And some of the things that, you know, were tied to it are, you know, privacy, shade, visual appeal. So we're going to build off of this and try to find out more about how can we design fuel treatments that are accepted by the public. And this is just an example of some around Anchorage. Hey, they can produce berries, lots of cranberries in this one. Moose, you know, you can see wildlife. People don't like so much the piles of wood that sometimes get left behind. Money sometimes does run out. And so overall, there'll be workshops, you know, these interviews that we're going to do, vegetation surveys that we talked about, more vegetation surveys and new field treatments and manipulations, the household surveys, choice experiments, then the cost benefit analysis, and wildfire modeling by Chris Moore. And so lastly, we're going to maybe try to look at some photo estimates for fuels. You know, there's this photo load, and there's a new paper that just came out with NIDAR photos. So walking along a transect and taking pictures looking directly down. We're really interested in that. So if anybody has used any of these, has any comments about them, feel free to reach out to me because I'm interested in it, and I want to try to use a method that could be picked up by other people and useful for research in Alaska. And so with that, I can take any questions or comments or turn it over to Michelle. Thank you.
All right, any questions in the room? Not seeing any in the room. Anything online? Chris Mace has a question.
Hey, Chris Mace here. I just wanted to say thanks for the presentation. I'm curious, the funding source for this work. It's a very interesting work, and I'm just curious who is going to pay for it.
It's the National Science Foundation. They have a Navigating New Arctic call that's been out for the last couple of years. So that's the sole source of funding for this.
Okay, I don't see any questions online and no more questions in the room. Melissa, go
All
for it.
right. Hopefully I share the right screen. Let's see. Just 1 second. Oh, shoot. Okay, does everyone see the right one? Not the notes.
Yep, we got a picture of a big fuel break.
Okay, great. So like Jen said, I'm on the ecological team for this project. I work as a research assistant in Michelle's lab at NAU. And I'll be going over some of the results from previous research we've done in these fuel breaks. And I actually gave a presentation about this last year at the, this seminar or this conference, but we finalized the results, and this paper is actually in review right now in forest ecology and management. And then I'll go into some of the current research that we're doing for this new SAFRR project. And overall, our primary objective for this SAFRR work is to assess the short and long-term drivers of post-treatment succession, fuel accumulation, firefighter egress, and any other variables that our SAFRR group identifies, and also that land managers and fire practitioners think that are important to identify in these fuel breaks. So in our previous research, we had two overarching research questions. The first is how do successional trajectories of tree dominance, understory composition, and permafrost change over time in these treatments? And the second is the surface fire behavior change over time in these treatments, and are they effective at reducing fire behavior relative to an untreated black spruce stand? And to address these in 2018, we remeasured a network of thin and shear-bladed sites across interior Alaska. And in the shear-bladed sites, all above ground biomass was removed. And in our study sites, most or all of the organic matter was also removed in these shear-bladed sites. And they were previously measured in 2012 and 2013 as well. And each site was also paired with an untreated black spruce stand for comparison. And here's just an example of some of the sites we visited. The top panel is when we visited them in 2012 and 2013, and the bottom is when we visited them in 2018. This thin site is a site that's near Delta Junction, and the right is a site near Fairbanks off of Cache Creek Road. And at each of these treated sites and at each paired untreated site, we established two 20-meter transects. Along these, we measured seedling density, vegetation composition and ground cover, and soil organic layer depth and thaw depth. We also modeled surface fire behavior in each of these treated sites and at each untreated site at the below average, average, and above average fuel moisture. We assessed how fire behavior changed over time in all the treated sites. And we also compared fire behavior in treated sites to fire behavior in an untreated black spruce stand. And we chose to only compare fire behavior in these treated sites to the black spruce stand, since this is the fuel type in Alaska that experiences the most extreme fire behavior. And I won't go into the modeling very much, especially since we're a little short on time, but I'll just give a really brief overview about what we did. So we did the modeling in Behave. For the treated sites, we used a combination of site photos, field observations, and our understory measurements to classify each site into a Scott and Bergen fuel model using the Alaska Fuel Model Guide. We used an average summer 20-foot wind speed for Fairbanks. And then we used a site-specific wind adjustment factor for each treated site. And then for the untreated sites, we modeled fire behavior using the SH5, a TU3, or a TU4 fuel model, since each of these models has either been used in the literature or recommended for fire behavior modeling in this black spruce stand type. Okay, just to remind everyone again, these were the primary research questions that we posed for this project. So in these thin sites that we sampled, there was no change in seedling density over time, but seedling density was negatively associated with organic layer depth. And deciduous seedlings were the most prevalent at these shallow organic layer depths. That's shown here. We have organic layer depth on the X, seedling densities on the Y, and the point colors note the different seedling types. And even though thinning itself doesn't result in organic layer removal, in a lot of these thin treatments that we sampled, fuels were burned on site. And in these sites where fuels were burned at the site, this is where the most deciduous tree seedlings were observed. And this just suggests that severe disturbance of the organic layer in these thinned areas is important for promoting deciduous tree recruitment. And this is actually really important because it suggests we can nudge the trajectory of these thinned areas towards deciduous dominance if we disturb the organic layer. In these shear-bladed sites, there was no impact of organic layer depth on seedling density. And this is likely because the organic layer was really shallow or even completely removed in all of these shear-bladed sites that we sampled. And deciduous seedling density did not change over time, and that's shown here in the left panel. But conifer recruitment persisted, and that's shown on the right panel. And this continued recruitment of conifers was really surprising to us because it's been really well established that after a fire, for example, after fire, tree seedling recruitment occurs within just the first few years on these disturbed organic soils. But even though there was this persistent conifer recruitment over time, you can see from this figure that deciduous seedlings really dominate these sites. And that's shown by this really large range of y-axis values for deciduous seedlings. And this can just be explained by really high deciduous tree recruitment on exposed mineral or shallow organic soils immediately after treatment. So understory plant composition and ground cover was also similar in the thinned and unmanaged sites, but it differed from that in the shear-bladed sites. So that's shown in this figure. This has the results of a community analysis of understory plant composition and ground cover in 2018. So each point here represents a site. The blue points are untreated sites, the brown are thin, and the shear-bladed are yellow. And sites that are more similar in composition group more closely together. And because these ellipses for the thinned and unmanaged site overlap, that means their composition is really similar. And in both of these thinned and the unmanaged treatments, they are generally dominated by mosses, lichen, and evergreen shrubs. And these shear-bladed treatments tended to be dominated by grasses, tall deciduous shrubs, and a ground cover of litter. Oops. Okay, understory composition also changed over time in these shear-bladed treatments, but it didn't change over time in the thinned. So that's shown here. This also has the results of a community analysis of understory plant composition and ground cover in only the shear-bladed treatments. The point colors indicate years after treatment, or the light points are older sites, and then these dark points are younger sites. And then the arrow points in the direction of change in vegetation composition over time. And you can see that as these treatments age, there was a shift from forbs and equisetum and mineral soil in the understory to a greater abundance of grasses, deciduous shrubs, and litter. And this essentially suggests that both fine fuels and fuel loads are increasing in these treatments as they age. In both treatments, there was also an increase in permafrost thaw depth over time, shown here. We have years after treatment on the X and thaw depth differences on the Y. Thaw depth difference is the thaw depth in the treated minus the unmanaged sand. So if it's above 0, that means it's greater in the treated sand. Thaw depth also decreased with increasing organic layer depth, shown here with organic layer depth on the X and thaw depth difference on the Y. And this just indicates that disturbance of the organic layer is really driving these increases in permafrost thaw. And you can also see from this figure that the organic layer was a lot shallower in these shear-bladed treatments. And it was often completely removed in shear-bladed treatments as well, as just indicated by all these 0 values. But even though thaw depth increased over time in both of these treatments, it was a much greater in the shear-bladed areas, as shown in this figure where we have treatment on the X and thaw depth is on the Y-axis. And this suggests that thinning is a better treatment to implement in areas of ice-rich permafrost if we want to reduce permafrost degradation and ground subsidence. Okay, getting into the fire behavior modeling results. In these treated areas, we didn't see a change over time in surface rate of fire spread. And that's shown here with years after treatment on the X, rate of spread is on the Y. The different point colors note the different Scottenberg and fuel models. And the shear bladed treatments are on the left panel and the thin are on the right. We also didn't observe a change in flame length or fire line intensity over time, but I'm just showing this here for simplicity. And because in our understory composition analysis, we observed an increase in fine fuels, such as grasses, over time, we also expected rate of spread to increase, but that was not detected in this fire behavior modeling. And this lack of modeled fire behavior change could just be due to the limitations of the basic fire behavior fuel models and or the type of data that we collected in this study. And so in this new SAFRR project, we plan to address this by taking more fuel specific measurements, which hopefully will allow us to more systematically classify these sites into fuel models, or even modify model parameters if we need to. Okay, lastly, our surface fire behavior modeling results show that treatment effectiveness at reducing surface fire rate of spread, flame length, and fire line intensity really depended on the fuel model that we used for black spruce. Here we have fuel moisture on the X and rate of spread is on the left panel, flame length is in the center, and fire line intensity is on the right panel. The blue points here denote fire behavior in a typical untreated black spruce stand, with each shade representing a different fuel model. Once again, the thin sites are in brown and the shear bladed sites are in orange. And this just highlights some uncertainties about the efficacy of these treatments at reducing surface fire behavior, especially when we're just modeling fire behavior and we don't have empirical observations to compare these modeled observations to. Okay, just to recap, we saw that there was high seedling recruitment at shallow organic layer depths and thinned areas, which could shift their trajectory towards deciduous dominance. In shear bladed areas, there was persistent conifer recruitment, but they're all following a deciduous trajectory. Thinning did not modify understory fuels, where shear blading did, and fine fuels and fuel loads increased over time in shear bladed treatments. Both thinning and shear blading resulted in an increase in thaw depth, but thaw depth was greater in the shear bladed treatments. And removal of the organic layer was a primary driver of increases in thaw. There was no change in surface fire behavior over time in either of these treatments. And in shear bladed areas, this did not agree with our multivariate analysis of vegetation change. And lastly, the effectiveness of these treatments at reducing surface fire behavior really depended on the fuel model that we used for an untreated black spruce sand. Okay, and with that, I'll move briefly on to our proposed fieldwork for the SAFRR project. So our overarching objective, like I said before, is to assess these short and long-term drivers of vegetation and fuel recovery across these field treatments, and then 3 ecoregions that Jen showed in that map. And we also, just in general, want to understand how these field treatments modify ecosystem structure and function. And we really want this new research to be informative for land managers in Alaska and for fire modelers. So any input from this group about what we are doing or what we should do would be appreciated. And we have 3 components of this study. We have an extensive survey component, we have intensive surveys, and then we have a successional intervention experiment. And here's just that map again that Jen presented earlier, but I just wanted to reiterate that we're doing work on the Kenai Peninsula, we're doing work near Fairbanks, and then also in Eagle and near Whitehorse for all components of this ecological part of the project. For these extensive surveys, we plan to take widespread measurements of ecosystem structure and fuels and treatments of various ages across all these ecoregions. Some factors we plan to measure are site characteristics such as moisture class, aspect, canopy cover, and then we also want to classify each site into a vegetation class using the Alaska Fuel Model Guide. We'll quantify woody fuels using a brown transects, and then potentially these other methods that Jen brought up previously. We'll also measure vegetation composition and ground cover, seedling density and composition, tree and tall shrub composition and characteristics. And then for these trees, we'll also measure canopy structure for fire behavior modeling, soil depth, thaw depth, and ponding in these sites. And then we also want to get at access and visibility, potentially using horizontal cover or a scale of accessibility. In these intensive sites, we'll do pre and post treatment measurements of ecosystem structure and fuels. And this is really to get an idea So really to quantify immediate post-treatment effects in these fuel treatments. And we'll be using the same sampling protocol here as we will be using in the extensive sites. And we're partnering with the TCC and Eagle to do this part of the project. We're also working with a crew in Whitehorse. We've identified some sites on the Kenai to do this, and then also some sites in the interior. And then lastly, we have this successional intervention experiment where we will manipulate these treatments to see if we can nudge their trajectory towards deciduous tree dominance. We'll do this at young sites and old sites. So young sites are considered anything for less than 10 years old, at least for this component of the project. We have 5 different experimental manipulations that we want to implement. So we have a control, a scarification, the addition of deciduous tree seeds, scarifying and seeding, and then fertilizing, and then removal of conifers. And then in the older sites, we'll do something similar, but instead of adding deciduous tree seed, we will plant deciduous tree seedlings. And lastly, just to recap, some of the things we really hope to gain from this SAFRR project and what we want to learn is what are the drivers and rates of vegetation and fuel recovery across these treatment types in these ecoregions. And how can this inform what management interval is needed in these treatments? We want to understand the controls on post-treatment succession and how we can manipulate these treatments to nudge their trajectory towards deciduous tree dominance. We want to better understand the impacts of these treatments on fire behavior in the short and long term. And then lastly, just how the design of these field treatments impacts their value for multiple uses, including firefighter egress, forest health, and landowner satisfaction. And with that, I'll take any questions. People aren't too hungry to wait for lunch.
Thanks, Melissa.
Yeah.
Any questions in the room? Tom St. Clair has a question.
I have one.
Go ahead.
Yes, it's Charlie Sink from Schmidt. So when you're going to nudge the conifers out, the soils that the black spruce is on, that's more favorable for black spruce as opposed to deciduous. What do you think your success would be?
In
The sites that are predominantly black spruce that you're trying to replace.
Yeah, so deciduous trees and deciduous trees seedlings recruit really well on mineral soil. So we want to see if the disturbance of this mineral soil will promote this trajectory of deciduous dominance. That's what we're hoping to get at by scarifying the soil in a lot of these field treatments and adding the deciduous seeds or the seedlings.
Okay, on the scarification. Okay, thank you.
Yeah, thanks.
Yeah, so this is Tom St. Clair, and my question has to do with characterizing fire behavior, and if there are any, you kind of showed a little bit the issue with using those Rothermel fuel models to characterize these fuel treatments. But did you find any other fire behavior terms that might be more useful in describing the differences between the fuel treatments?
So describing their differences in fire behavior.
Yeah, it might be a loaded question. But
Well, yeah.
I wonder if you guys explored any other terms.
I think with this new project, we're planning on just taking a lot more measurements, and then hopefully with that we can better classify them into a fuel model, because it seems like for this previous project when we were classifying them, we didn't have really as much information as we would have liked. I think like we didn't do a Brown's transect for that last research project. So I think by doing more intensive measurements, we could better classify them into a fuel model. And we also plan on classifying them using in the field, and then also after we do work in the field to see if our results vary or if our classification varies. And I don't know if that really answers your question, but.
I guess I was wondering if you thought about things like spotting potential.
Oh, yeah.
Factor, resistance to control, ability to construct a fire line in the fuel pipe, receptance to water and fire line chemical use.
Yeah, we want to model canopy fire behavior this go around. And then it seems like we also want to get at access, and we haven't decided exactly what the best way to do that is in the field, but I think we're going to experiment a little bit this year and take a bunch of measurements and see if any of them might be relevant. And I don't know if other people who work more in the field or can do firefighting up in Alaska, but if people have input about how we can measure access, that would be really great.
Yeah, I don't know how to measure it. I just know that is more useful in describing the treatments than the fire behavior surface spread model.
Okay.
Yeah, I'm willing to talk to you guys a little bit about it.
Yeah, that'd be great.
Any other questions in the room? I have a quick question, Melissa. I actually just saw your the agency review for the DMLW for your living fuel break for the conversion from spruce to hardwood or establishing hardwood in these fuel breaks. And I appreciate that because I think sometimes the fuel breaks that we have, we call them, or we have been, at least today, been calling them clear cuts, but clear cuts are supposed to have a regeneration objective. I think these are more conversions from forest to non-forest. So it's good that we're looking more at stand conversion and still keeping it in forest. Whether or not that's operational, I guess, will depend on what the firefighters do. But I was wondering what, so for it looked like for your old fuel breaks, you were going to plant some birch. So what is your standard for the height of those seedlings when you plant them?
Yeah, so we're honestly just doing pretty small seedlings this year. I think they're going to be about a half a foot maybe in height. And we don't really have like a good reason to do that. We just kind of are going to experiment and see if they survive and how they do this summer, because then next summer we'll redo it again and see, because if it works this summer with these smaller seedlings, we'll just do the same thing. And with aspen, we want to do aspen too, but we're going to do root cuttings and see if those work as well. And we know that a lot of people in Whitehorse are doing it, but they're planting aspen in Whitehorse already in these field treatments, and they're using trees that are like over a foot tall for aspen.
Okay, thanks.
Yeah.
Chris Maish has a question.
Thanks. Hey, I was just wondering what time of year do you intend to do the planting? I was once involved in planting birch out in Holy Cross in the month of June and on permafrost sites after fire, and the ground was still frozen hard as a rock a few inches down. So I was curious what you guys were thinking.
Yeah, that's a good point. We're planting them at the end of July.
You probably should have better luck then, I think.
Yeah, we're actually working with a local grower in Fairbanks. He's growing all the seedlings for us, and he was like, don't plant them in June. It's going to be way too cold. So,
Right. Well, based on my experience, I'd agree, at least especially on the permafrost sites. Literally ice just inches down.
Yeah, good to know.
The second question is on the fuel models. Are you using CFF-DRS models, or I wasn't familiar with the metrics that you use to describe the fuel models, or TU7 or something like that? So maybe you could explain that a little bit more, please.
We're using the Scott and Bergen fuel models, so the 40 fuel models, and we classified each site into one of those. And the fuel model guide to Alaska vegetation, I don't remember how many vegetation classes there are, but each of those, there's a few models, one or two fuel models that are representative of each of those vegetation classifications. Does that answer your question?
Chris is giving me the thumbs up.
Okay, cool.
All right, any other questions? All right, well, thanks, Jennifer. Thanks, Melissa. It was a great presentation. And I'm going to turn it over to Ed here.
Hey, thanks again, Jennifer and Melissa. One of the nice things about having a hybrid meeting is you can join us without joining us. And the same goes for Mark Castle if you're still on. So thank you for your presentations. And we are going to take a lunch break. And we'll come back at 1 o'clock. This still gives us plenty of time for lunch. Same for you guys virtually. And so we will come back at 1. All right, thanks.